Test, test. Okay, people are online. Can you hear me? All right, thank you. All right, good evening. Let's get started with the greeting vector. Let's continue on that subject. If you have a function, I'll use a function 3 variables here, okay, just to do this quick review. Then the greeting vector for function f is defined as del f and equal to partial f partial x, partial f partial y, and partial f partial z. Okay, that's what we have learned about the definition of what greeting vector is, right? So I didn't even talk about what's the meaning greeting vector, how do we interpret it? So that's what we're going to cover today. So this function 2 variables, 3 variables. Or if you have a function 2 variable, right? So then it simply just become okay. So basically, you can clearly see when you have a function 3 variables, you get a 3D vector. And then here you get a 2D vector. So let's take a look at an example of a 2D of a function of 2 variables. So here's a function, f of xy equal to x squared minus y squared. And if you remember, this one is a surface of a saddle, right? So saddle surface, you have x squared minus y squared. Okay. The question is, let's say to find the del f and also del f at 1, -1. Okay. So del f, you're taking partial derivative now. Partial f or partial x, partial f, partial y. So 2x -2y is the greeting vector. It's not a constant because you plug in different xy value, then you get a different vector. Right? So in this case, I'm looking for the vector at 1, -1 location. So x equal to 1, y equal to -1. You plug in into this vector here, you get 2. And -1 plug into the y, now you get another 2 here. So you got 2, 2 as this greeting vector. Okay. So the question, I think I raised this question at the end of the previous lecture. When you have a greeting vector like this one, you specifically got it. So how do we graph that, and how do we present it in the graph? So this one I can certainly sketch that because it's 2D. Actually, it's not that easy to sketch. It's a saddle. So, but the saddle surface, right? Hand drawing it is not as ideal as. I will show you what the saddle looks like. All right? That's the surface, the saddle surface. Okay. Now, where's the 1, -1? So you look into, so x equal to 1, y equal to -1. So it's a point somewhere over here, right, in the coordinate system. That's 1, -1 location. Okay. The gradient vector we find is at the location 1, -1. Okay. So the point here is once you get the vector here, then you need to sketch this vector, okay, at the location. So how do we do that? I'm gonna do this using, because this is a 2D vector. So let's just look at from the top. Okay, this is x, this is y. If I look from the top, xy plane, then first what you need to find out is this 1, -1 location. So x equal to 1, y equal to -1. Okay, so this is the 1, -1. Once we found this out, the next step is to look at the vector 2, 2. Now, if I just ask you to sketch vector 2, 2, so what you typically would do is, right, you find 2 here, you find 2 there, then you create a vector, right, 2, 2. Okay, so this vector from 0 to this 2, 2 here, that's the vector 2, 2. However, but this time the vector is attached to the specified point 1, 1. So you need to move this vector parallelly without changing its direction, without changing its magnitude. I move it to the starting point 1, 1, 1, -1 here. So this is the actual location of this gradient vector. Okay. So of course, as you can clearly see, you have a surface, and then you have this gradient vector, right, attached to there in the xy plane. So the other graph in the lecture notes is much better explained by superimposing the contour plot, okay, in the xy plane. So all these curves here are contour plots. The 1, -1 is right here, and this is a gradient vector, right, pointing to this way. Good. And we can even come back to this graph, okay, just to understand a little more. Actually, once I give you the meaning of this gradient vector here. Okay, so now I'm going to write down a statement without any proof, okay, and I will come back to this, the statement. Okay. Let's call it comments here. So I want you to accept what I would write after this comment, okay. But we'll be able to prove that, and we'll be able to prove the correctness of the statement. So the statement is basically, it's about the meaning, okay, the meaning of a gradient vector. It's like a partial derivative. You know, we talked about what's the geometrical meaning of a partial derivative, right? So here we want to get similar meanings for gradient vector. First statement is that gradient vector, okay, gives, it's a vector, right? First, so you had to firmly in your mind believe that this is a vector. It's called a gradient vector, but it's a vector essentially. Okay, for any vector, you have two information. One is the direction, the other is the magnitude. Okay. So then the gradient vector is a direction. Okay, it gives the direction of the greatest increase for function f, or in this case, z equal to f, right? Yeah, it can be f here, not restricted to 2 variables. It can be 3 variable, 4 variable, it doesn't matter, you know. Okay. But it's that function f. For example, in function 2 variable, we use the z equal to f of xy. That's the first statement. So now I'll come back to the statement, okay? And then I'll say this a little more here. The second statement is, okay, so magnitude of the gradient vector. Okay, the first statement is about its direction. The second statement is about its magnitude. And the magnitude of this gradient vector gives the rate of increase. Okay. And I often joking, when whatever course you're taking, okay, and you probably will forget most of the course, the content, after months or 2 months, and not to see after a year. And after 10 years, you don't use it, that's it, right? you don't remember much of it. However, right, for every course, maybe not every course, but for some course, there's always something that you should remember, even for the rest of your life, And this is something like this for this course. Okay, what is the meaning of a gradient vector? So if I had to ask you, what do you have to remember about Lecture1448 after you graduate? First thing is this. Okay, so what's the meaning of gradient vector? So let's go back to this first statement. Its direction gives the direction greatest increase for function f. Okay, so for example, let's go back to this example here, right? Here's a function f, okay, or z equal to f of x, y. Okay. And then you have the gradient vector pointing to this way here, right? So according to my first statement, which means if you're initially at this location, then if I change from the initial location along the direction of the gradient vector, then what? Then the function f, which is this surface, should increase the most. And that's what it means. So in other words, let's just consider you have a small person here, and then you have another guy right on top of the surface. Okay. Wherever this guy moves, and the one on the top will be moving accordingly. So if this bottom guy moves in the direction, don't move too much, just a little bit, okay? Yeah. If it moves in the direction given by the gradient vector, then the guy on the top of the surface will actually start climb up the fastest, right? You think about a mountain. So you could climb this way, climb that way, right? If you're suppose you're controlled by someone on the floor, giving you a command of X, Y. So which rate do you want to climb the fastest? The direction given by the gradient vector. Okay. So that's basically the first comment. And then the second comment, the magnitude of this gradient vector is the rate of change. So you would say, okay, so if I go in that direction, then how fast am I going up, right? What's the rate of change? That's given by the magnitude of this gradient vector. So it's a very, very important vector, as a matter of fact. Okay. So let me show you an example here. Now I do have a good way to prove it, but just for now, we want to leave it until we finish the directional derivative, and then we can come back to this two statement and see whether the two are right or not. But of course, they are right, right? So I'll be better off to prove that once we finish the directional derivative. So let's use a slightly different surface, okay? But I'm gonna touch this in a two different perspective, okay? So I want you to focus at it here. So of course, if I sketch the surface, we have already demonstrated it's a paraboloid, right? A paraboloid. So, and that's a much easier surface to sketch than settle. Okay, so I'm going to look at, I'll call this case number one. In case number one, I'll calculate the gradients of this function f. So I get 2x, 2y, and then I'm going to calculate the greeting vector at 1, 1. So get 2, 2. Right. All right, so I'm going to do exactly the same. This is essentially repeat what I have done. I'm going to go find this 1, 1 location. And then I will attach the greeting vector 2, 2 to the location 1, 1. 2, 2 is a vector basically pointing this way here. That's 2, 2 vector. There you go. Okay, so if I go back to the two statements, so then what it means is if I go in this direction, right? So let's say at 1, 1, you are over here on the surface. Then once you go in the direction given by the greeting vector, okay? So suppose you have a person, one is the ground, one on the surface. So this person A will actually, right, climb up in the fastest fashion if you go in the direction given by the greeting vector. Okay, that's basically what we have covered. Any question on this simple case? All good? Yeah, understand that. So second case, okay, is I will change my perspective a little bit, is that I'm going to define myself a new function, right? Call it w equal to z minus f of xy. And then this new function apparently, right, because I have f of xy, so it's z minus x squared plus y squared. Good? Okay. So I want you to keep your head clear is once I define my w here, okay? So make sure you know that w is not the same as your original z anymore, right? Yeah, this is a function of 3 variables. Can you sketch w? No, you can't. Okay, I think I repeatedly said this because the function 3 variables. But you can certainly try to visualize, not really visualize, but you try to understand the w using the concept of what? Level surfaces. Okay. So basically, if you let w equal to 0, and then you obtain the paraboloid surface. But this is only one level surface, right? So this is a level surface for function w. If you let the w equal to different constant, then you get a different level surface. Right? So we learned that. So now what I'm going to do is I'm going to calculate the greeting vector for the function w. So if I calculate greeting vector of w here, which is defined by this function, according to the definition, greeting vector, you have a partial w partial x, partial w partial y, partial w partial z. That's the definition of greeting vector. Okay. So can you help me fill out the blanket here? Here's your w. What is partial w partial x? Two x minus, right? Don't forget a minus here. What about partial w partial y? Good. What about partial w partial z? 1. Good. Okay, so basically, the first two terms, one is negative fx, one is negative fy, and then 1, right? Yeah. because this part is a function f. You got the negative 2x, or you got a 2x by calculating partial f over x. And you got the 2y from partial f over partial y. Okay, so that's your del W. Okay. So what's the usage of this one? Okay, this is what I'm going to emphasize here. All right. So let's get back to the parabola graph right here. So this is the graph z equal to f of x, y equal to x squared plus y squared. Now, if I ask you, can you calculate the grading vector of w at 1, 1, 2? 1, 1, 2. All right, so you can certainly calculate that. You plug in x as 1, plug in y as 1, plug in z as 2, but you don't have any z, so keep the 1 there, right? So you get what? Negative 2, 1. So you got a grading vector. And this grading vector is attached to 1, 1, 2. So where is the point 1, 1, 2 then, right? So let's look at it. This is where's the point 1, 1, 2. I'm going to use this one to check. If I plug in x equal 1 here, y equal to 1 here, guess what? I got a z equal to 2, right? So this 1, 1, 2, the point that we're asked to calculate the grading vector, happen to be on this surface here. Which surface? Z equal to x squared plus y squared. So 1, 1, 2. If I had to do it, you know, this is 1, and then 2 is right here. There you go, right? So this is 1, 1, 2 right here. Okay. Then this is the grading vector. So I'm going to sketch this grading vector according to the practice I have done for the 2D. I will sketch this grading vector and then attach the vector to this 1, 1, 2 point. I mean, this is a 3D vector. You do exactly the same thing. So how do you sketch? If I just say, can you sketch negative 2, 1? So what do? You go find negative 2 here. You go find negative 2 here for x and y. Then you find 1 for the z component. So then you go find basically the coordinates for negative 2, 1. Then you create the vector. So this vector is negative 2, 1, right? But now what do? We move this vector and then attach to this point, and without changing its direction and length, okay, and then you draw the grading vector at that location. So far, so good? Good. So now let's get back to my 2 comments, right? What are the 2 comments? The comments about the grading vectors. Number 1 comment, grading vector give me the direction of the greatest increase for the function f. I saw SFF in that case, but in this case, which function am I calling it? So this vector here, grading vector, give me the direction of the greatest increase for which function? Z? W? W, okay? So that's something you had to be very crystal clear, okay? So this gives direction for the greatest increase in W. But where's W? I'm not able to sketch W, right? However, if you think of the W in the level surface perspective, you see here, this is a level surface. You get it by letting W equal to 0. And then the gradient vector tells you you want a greatest increase of W, you got to increase, you got to go from 1, 1, 2 in that direction. So basically, if you go on that direction, then you end up maybe on the next level of the level surface. And the next level surface might be what? W equal to 1 or W equal to 2, who knows, right? But that's the direction the level surface is going. So basically, the level surface is more or less like a layers of a level surface, right, on top of each other. Okay? It's not so the direction indicating the increase in the W. Okay. So that's good, right? So my point here of presenting two cases is when you have a function, right, like given here, you could create two different gradient vectors. One is a 2D, purely based on the F at here. Another one is a 3D. By constructing a W like this, you get a gradient vector. Okay. And this gradient vector, in our case, most of the time, the coordinates will be attached to that surface. And then you can create this gradient vector at here. Okay. And we have even one more point to make the next. And the gradient vector that's calculated at here is perpendicular to this surface. Okay. And the gradient vector calculated over here is perpendicular to the level curve. Okay. So we're going to look at that next. Okay. So that's actually the nature of gradient vectors at here. So always, so some of the questions, the reason I'm pointing this is because some questions you need the gradient vector based on the 2D, partial f, partial x, partial f, partial y. And in some cases, you need a gradient vector for the surface. Okay. So that's why we need to be clear what gradient vector the question requires us to obtain. All right, so let's go back to the two things I actually just said it. Right? First thing is, what's the relationship between this gradient vector and level curves? Okay. So I'm basically going to write down like a two, you can call them a theorem or, or principle, doesn't matter, but it's essentially as a result, a conclusion that we can make use of. So given function of two variables, then if you calculate the gradient vector, and this gradient vector is perpendicular to level curve. So what's the level curve? Level curve means when you let z equal to a constant, then you create a level curve. I think in a class I demonstrated, how do you generate level curve? You have a surface, then you let z equal to constant. Basically, you're creating a plane at a different height. Then you slice the original surface. Then you create a whole bunch of curves, intersected curves. You drop all the curves to the plane, xy plane. Then you have these level curves, also called contour plots. Okay. So that's the first statement. I will actually try to prove that next. Okay. And this statement, the first statement is equivalent. Okay, it's equivalent statement to the second statement. When you see a vector perpendicular to a curve, it's equivalent to say the vector is perpendicular to the tangent line of that level curve at certain points. So these two statements exactly the same. So what this essentially basically means, let's for example, you have a curve, and then you have a tangent line to the curve at a certain point. Then you can certainly create a vector, right, perpendicular to this line at here. And then this line is equivalent to when this line is perpendicular to the vector, we can equivalently see that this vector is perpendicular to the curve. Okay, so that's what it means. All right, so let's try to provide a very simple proof at here. And see how this statement is created. And before we do that, I just want to illustrate again about the level curves concept. If this is a general surface at here, then you can slice that using z equal to c. So then you basically will have maybe a certain curves, right, intersected between the plane and the surface. Then you can drop that to the xy plane. Right? So you get a level curve because every point on a curve share the same altitude, right? That's why they call it level curve. All right, so then if I look down from the top, I might see some sort of a curve, a level curve like this. So let's suppose, and this is a level curve f of xy equal to c. Okay, so that's one of the level curve. So I'm trying to prove the gradient vector is perpendicular to this level curve. Because it's a curve, then it's most probably we can use a parametric equation to describe this curve. So let's suppose the level curve has a parametric equation using r of t. So x of t, y of t, right, like that. So what that means is this x and y here in the function f basically can be replaced with x of t, y of t, and equal to c. For example, if level curve is a circle, then x equal to r cosine, r depends on the radius, right? R times cosine t, then y could be r times sine t, and that's an example. Okay, so now I'm going to take derivative of this function and take derivative both sides. So take derivative both sides with respect to t. So what we're going to get, where are we going to get? This side is easy, it's constant, so derivative constant is 0. And this side, you're taking derivative with respect to t. And f function is a function xy. Xy are function of t. So then I guess the chain rule will come in handy. So partial f, partial x, dx over dt plus partial f, partial y, and then dy over dt. There, right? So you got this based on the derivative. The left side can be rewritten as partial f, partial y vector, and then dot dx, dy, dx dt, and dy dt equal to 0. Good. So can you tell me what is the first vector? What's the first vector here? Yes. Gradient vector, exactly, right? Del f, that's gradient vector. What's the second vector? Dx dt, dy dt. How would you get the second vector? At least based on the given condition here. Yes. The tangent, or dr over dt, right? Yeah. So now you have the dot product equal to 0. Do you remember when two vectors are dot product equal to 0, the two vectors are what? Perpendicular. So if I relate back to the wording, the greeting vector is perpendicular to the tangent vector to the curve. And that's exactly what we're looking for, right? You create a tangent vector here. Then you create a greeting vector here. And these two are perpendicular. Not necessarily always pointing this way, but anyways, just for illustration, right? Yeah. So that proves this statement. Greeting vector, okay, for function of two variables, and you have surface, you can create a 2D greeting vector. Then that 2D greeting vector must be perpendicular to the curve, to the level curve, and also must be perpendicular to tangent line to the curve at a certain point. Okay, that's the point. Okay. I do have time, good. So my other statement is for function of 3 variables when you have a 3D greeting vector. And I said that greeting vector is perpendicular to that surface. Right, so let's look at this one here. And first of all, any questions on this part of the statement? Okay. All right, so now let's consider the next one. So let's see, we have a function of 3 variables, W. Then we have calculated the del W. Okay. So this time I'm using a very generic W, right? It's not the Z minus f of xy. You know, that's not a very generic. So this is generic function 3 variable. So if I calculate greetings, I can just simply calculate del W as if you know, partial W, partial X, partial W, partial Y. The statement is del W is perpendicular to level surface W equal to C. And W equal to C, basically W, let's write it, Wx, Y, Z equal to C. You let it equal to constant. Or equivalent statement. Okay, the two equivalents, another equivalent statement to the first one is del W is perpendicular to a tangent plane of the level surface at a certain point. So when you have a level surface and you calculated a greeting vector at a certain point, and you get a point on the surface, and you can certainly create a tangent plane to the surface at the location, right? Then the del W there is basically it's a vector perpendicular to the tangent plane or perpendicular to that level surface at that location, right? So if I use that example, so let's say, for example, W equal to Z minus X squared minus Y squared, that example we demonstrated. I let the W equal to 0, then I got a level surface, which is this one, the paraboloid. And then we calculated del W. We also calculated at which point? At 112. Okay. And 112 is right here. And we got a del W pointing to that way. Okay. Then at this location, you can certainly create a tangent plane, right? You can visualize in your head. I draw a very small patch representing the plane tangent to the surface at that location. So according to the statement, this del W is perpendicular to this plane here. Okay. Okay, so now this one, the proof And I understand mostly students don't like the proof most of the time. I want you to read the page to get a proof yourself if you're interested. But otherwise, if you're having trouble, you can always come to me. Can you remember the page here? I do have a very simple, it's not very complicated proof, just no more than 4 lines of code math here. So read the proof in the lecture. Okay. So that should, it's not very difficult to understand. So this is actually quite an important funding in here, okay? So you actually can relate to one of the things we learned in total differential or in the linearization. Okay. Now in linearization, we also mentioned when you have a surface, you can linearize the surface at a certain point using a plane, right? Using a tangent plane. And we use the Taylor series expansion, right, to create for multivariable function to create that linearization, okay, which actually will be the same over here. So I'll show you an example. Okay, let's consider a surface x squared plus y squared minus z squared equal to 4. So here's a surface. Now, if I have to think of this as a general case, right? So sometimes it doesn't really give you more information other than that. But in your head, you probably should think of as this. For example, let w equal to x squared plus y squared minus z squared, and w equal to 4. Right, so then you get this one, which is a level surface, right, given by this function. Okay. So that's how that level surface is acquired. The question is, can you find a tangent plane at 2, 1, 1? So basically, can we find a tangent plane at 2, 1, 1? So this kind of relates back to our earlier lectures, finding lines and planes in 3D space, right? The case is tangent plane, right? So basically the plane is tangent to this surface at 2, 1, 1. So before I talk about how to find a plane, the first thing that we probably should actually checking is you have a level surface. Okay, without a computer, it's probably not that easy to graph it. But anyways, just suppose you have a graph, right, surface in 3D space. And now you have a point 2, 1, 1. So the first thing you should check is this point 2, 1, 1 on that surface? Okay, so that's the first thing we should check. So let's do that, right? So check if 2, 1, 1 is x squared plus y squared minus z squared equal to 4. And how do we do that? Very simple. You substitute x, y value, x, y, z value into the left side and see if it's equal to 4, right? Yeah. So what do we get? So 2 squared plus 1 minus 1, that's your left side, equal to 4. So check. So this is a point on that level surface. So which is perfect because you see, you're required to find a tangent plane at this point to that surface. And guess what? If this point is not on the surface, then what's the point you do the rest of the work, right? So that's why the first step here to do this. If I give you a question, most probably that point will be on the surface. So you don't really have to check, right? But otherwise, you probably want to check. As a matter of fact, in one of the midterm example, I can't remember which year. So I created a question, I created a point, and I asked the student to get a tangent plane to the surface. So everybody followed the procedure perfectly until at the end, one student pointed out to me at the end, the point is not on the surface, you know. So okay, you know, as long as you got the procedure right, it's okay, right? So that's my bad, but usually you should do that, right? Just make sure we before proceeding. So then the next step is about the plane. So to create a plane equation, you stick to the formula and see what you need. All right, so this is how you create a plane equation. You need a normal vector to the plane. You also need a point on the plane. And that's the two information you need. Let's look at what we have. We said the plane tangent to the plane at this point. Great, perfect. So we already have 2, 1, 1. That's your point on the plane. What about the normal vector ABC to the plane? So how do we get a normal vector to this plane? Right, so you have a surface. And then this is a point. You need to create a plane, tangent plane at that point to the surface. So you need a normal vector to that plane in order to substitute into the plane formula. So what would be a candidate for this normal vector? Anybody? Yes? Grading vector, exactly. Right? So you need to calculate the del W to get the grading vector at the 2, 2, 2, 1, 1. So del W at 2, 1, 1. And once you get this, it should be pretty straightforward because del W give you 2x, 2y, and then negative 2z. Okay, so you see, what's the W? This is W here, right? Yeah. You get this, and then you substitute 2, 1, 1 into this, and you get, what do you get? 4, 2, negative 2. Once you get this, simple. So this A here is 4, B is 2, negative 2. Right. There you go. That's your plane. So what we made a result is the grading vector is perpendicular to the level surface at the location, and equivalently, it's perpendicular to a tangent plane to the surface at the location. So that's how you can get the tangent plane. Okay. Good. So we're right on time. I still have just a little bit to finish the grading vector, but otherwise we're good. Okay. Any questions? All good. All right. So no lectures next Monday, no tutorial next Monday. We do have a quiz for next Friday. And to do the 5 quizzes as stated in the lecture in the syllabus, we need almost every other week, right? By skipping the reading break. Okay. So I think announcement will be put up on the canvas, same structure, same thing, but this time you'll get a little bit more time for scanning upload. Last time there are a few students email me their solution saying they ran out of time to scan upload. Now this time I will give you 10 more minutes. So I will not accept any email submissions. Okay, so do practice how to scan and upload. All right, have a good Thanksgiving. Hey there.
I might need a little bit of technical formulate question.
Yeah.
So for this one.
Yeah. Oh, stop recording.